Okay, here is an example of calculating radiation intensity at different distances using a scenario in the Sentinel lab to set the scene. Lights, please. Here we have this guy working in the lab who clearly should not be. And here we go, he's dropped a source on the floor again. Now this is an accurate representation of 0.02 microcuries, or 20 nanocuries, a very low activity iridium-192 particle. The particle on your screen is measuring exactly 740 becquerel, or 740 emissions per second. If this were, let us say, a 105 Curie sealed source instead of just a particle, the radiation alarms would be sounding and everyone should immediately evacuate the building. But this guy didn't. So the first step in quickly estimating his dose while we send his dosimetry to be processed is to calculate the approximate exposure rate at his distance from the source. Because every gamma-emitting isotope has its own constant, a known intensity at a defined distance per Curie, if we know the isotope and the number of Curies, or activity, we can establish a baseline to calculate exposure rate of any gamma source at any unobstructed distance. Now we will use two basic equations to do this. The first simply multiplies the number of Curies by the gamma constant to get the initial intensity. The second equation uses the known distance given to us with the gamma constant, divided by the second distance, squared, then multiplied by the initial intensity we got from the first equation. Believe it or not, we already have enough information to find out the exposure rate, or intensity, of this source at any unshielded distance. Let's collect some data, and we'll start with what we know. We know the isotope is iridium-192, and we know it is 105 Curies. This is A for activity. We also know that iridium-192 will always measure 5.2 R per hour for every Curie at a distance of 1 foot. This is the gamma ray constant, and 1 foot is your first distance. But because this dropped source is not 1 Curie, and rather 105, we first need to do a simple calculation using the first equation, which multiplies the number of Curies by the gamma constant. This is 105 Curies times 5.2 R per hour, which equals 546 R per hour at 1 foot. So now we know what the exposure rate is at 1 foot from this source, but this guy at the cell door is 3 feet away, and the inverse square law tells us that he is being exposed at an intensity that is much less than if he were at 1 foot. Now we use the second distance equation to calculate the exposure rate at 3 feet. Plug in the first distance of 1 foot, divide that by the second distance of 3 feet, and you get 0.33. Now square the answer. Multiply this by the initial intensity of 546 R per hour, and you get the intensity at 3 feet, 60.7 R per hour. If he had gotten out of there in a few seconds, as he should have, it wouldn't have been so bad. But if he stood in that same spot for just 5 minutes, he would have exceeded his exposure limit for the year, which is why it is so important to evacuate as soon as there's a problem like this. 60.7 R per hour is one thing, but his colleague who stayed to help was only 2 feet from the source. We can calculate the exposure rate at 2 feet by going through the same process. Plug in the initial distance, divide that by the second distance, square the answer, and multiply that by the initial intensity, and you get 136.5 R per hour. No good deed goes unpunished. If this guy stayed there for a little over 2 minutes, he's reached his yearly exposure limit. Not good. The same process can be used for any distance, provided there's no shielding between the person and the source. You can find out the radiation field this guy was standing in at 10 feet, or this one at 15, quite easily by following the same steps. Try to calculate the exposure rate for the worker at the well counter 10 feet away from the dropped source. Hint, it's much less than the rate at 2 and 3 feet.